Hello and welcome back. In this video tutorial, we'll be looking at the AP Physics 2 homework assignment, Electric Field Problems. In this homework assignment, we're going to be looking at 4 different problems in particular. Electric field simple, charge causing an electric field between two charges, and a charge on a string in an electric field. Let's begin. So for electric field simple, go ahead and enter your name and let's begin. You're going to be prompted with a charge at a certain location and a yellow electric sensor placed at some other position. Your job is to find, well, the distance to that sensor and then find the magnitude of the electric field passing through that sensor at that location and the direction of the electric field at that point. All right, let's begin. So the first thing I'm going to do is I'm going to map this on my picture. So at 71, I'm going to make a dot. And I have a positive 88.3. Now, I know that electric fields radiate out in all directions, like this. The only direction I really care about is this direction right here, because you can see this would pass directly to the left through my sensor. Therefore, the direction of the electric field at that sensor is going to be directed to the left. Now, the distance are, see, it's what, 10, 20, 30, 40, 50, 61 centimeters or 0.61 meters. So for step 2, we're going to find the magnitude of that. And let's go ahead and calculate it. The equation we're going to use is KQ over R squared. So we have 9 times 10 to the 9 times my value for Q is 88.3 times 10 to the negative 9 all over 0.61 quantity squared. Enter in your values. Newtons per coulomb is the unit. Go ahead and enter in your values and let's see if we can get this right. Okay, I got 2135.7 or 2136 newtons per coulomb to the left. Okay. Step 3, explain how we got the direction of the electric field. Well, again, electric field lines are directed outward, away from positive charges. And therefore, the electric field would be passing through the sensor directed to the left, since the sensor is on the left side of the charge. Okay, let's enter in our values and see how we did. So I got 0.61. Oh, no. Got to put 61 because it's in centimeters. So 61. And I got an electric field magnitude of 2136. Directed to the left. And there you go. Okay, so one question down. On to question 2. Now in question 2, we are going to be given a sensor with a field strength at sensor A. Using that information, we're going to have to find the charge at the origin and identify it as being positive or negative. Then, when we know that charge, we can calculate the electric field at a new sensor location, sensor B. So go ahead and enter in your name and let's begin. Okay, so you can see my sensor A is way over here. It's, let's see, 0.51. It's 1.5 over to the left and 1.4 up. So I am going to draw that in. So 1.5 over 1.4 up. There's my sensor. And notice the arrow is pointing away like this. That would indicate that this charge here at the origin has to be a positive charge to send the electric field out in all directions. So I know that that charge is positive. Now I got to find the value of that charge. Well, the distance from here to here is negative 1.5, and this distance from here to here is 1.4, and I believe this is all in meters. So I can use Pythagorean theorem to find that distance there. So I'll call R. Okay, so let's find R. R would be the square root of 1.5 squared plus 1.4 squared. I'm getting about 2.05 meters for my R. Okay, now my R squared would be 4.21, which is the square of that. Remember, I took the square root of 4.21 to get this value. So R squared can be handy because that's kind of part of our equation. All right, so now using the location of sensor A and the strength of the field at sensor A determine the strength of the charge located at the origin. So we basically have to solve the electric field equation for Q. So K Q over R squared, and we need to solve for Q. Now, in order to solve for Q, you have to get rid of the K and the R squared. Well, we can do that by multiplying both sides of the equation by R squared over K. In other words, the reciprocal fraction. Now you can see Q is by itself. So that's the algebra involved. Q, the charge, is going to be ER squared divided by K. Well, let's figure out these values. R squared we already have. E, we are told, is 1340. We can see it down here at the bottom. So we are going to go 1340 times R squared. Well, R squared, if you remember, was 4.21 divided by 9 times 10 to the 9. All right, let's put that in our calculators. No, put your values that you have in your calculator, but use mine as a template to kind of help you figure yours out. All righty, I am getting 6.2268 times 10 to the negative 7. Now, if I play around with the exponents here and I just kind of move a little bit over, I get 626.8 times 10 to the negative 9. Well, that would be 626.8 nanocoulombs. Right, so there's my charge. Now, using that information, let's figure out the strength of the electric field at sensor B. Same equation, okay, Q over R squared. Now we have Q. So it's 9 times 10 to the 9 times 626.8 times 10 to the negative 9 all over. You can see sensor B is located at 1.2 meters away. Okay, let's go ahead and put that in our calculator. And I'm getting a value for mine of about 3918 newtons per coulomb. Okay, now notice it since my charge is positive, it would radiate outwards in all direction, including to the right, passing through point B. My value is 3918. All right, and there we go. Hopefully you were able to get question two correct yourself. Move this down here. Okay. Question number three. Electric field from two charges. Now in this one, you're going to be given two charges. Let's draw them on the axes. Enter your name. All right, so I've got a positive charge at negative 1.4, so it's 407. Positive 407. And negative, so let's see, 15, 16, so it's 17, negative 675. 15, 16, 17, negative 675, and that's Q2. Okay. And I am told that my sensor location is at 1.2 meters down on the y-axis. So right there is, I'm going to call that point P. Okay, so what we need to do, we need to find some locations here. So I know that this is 1.4. So this is 1.4. I know this is 1.2. I know that distance is 1.7. And I need to find this distance here and this distance here. Okay, little Pythagorean term will help with that. And I'm going to leave them as r squared because it's, well, no, I'll just find r. Okay, so I got to find r in both cases, little Pythagorean theorem there. So let's put 1.4 squared plus 1.2 squared, square root that. And I'm getting 1.84 meters between Q1 and P. And 1.7 squared plus 1.2 squared, square root that, and I'm getting 2.08 meters between Q2 and point P on that side of there. Okay, now we've got our values. Let's figure it out. Okay, so I know since Q1 is positive, it's going to send an electric field line down in this direction through point P. I know that since Q2 is negative, it's going to send electric field vectors toward the negative charge in this direction here, toward. So in this first compass rose, we'll do that for Q1, okay, and then this one for Q2. So for Q1, we're going to have a vector pointing this way right here, okay, that we'll call E1 because it goes with Q1. And for Q2, we're going to have be in this direction here. We'll call this E2 because it goes with Q2. Okay. Right? We got to break these down into their components so that we can be able to figure it out. So once we find E1 and E2, we're going to have E1 kind of in the X direction and a negative E1 in the Y direction, right? Need that angle. Okay, same thing here. We'll need E2 in the X direction, and we'll need E2 in the y direction. And yes, we'll need that angle to be able to do that. Okay. By the way, finding those angles, just use a little bit of arctan. There's your theta for angle one, and here's your angle, which means that's your angle uh for the second one. So for the first one, it would be the arctan of 1.2 divided by 1.4. It's about 40.6 degrees. So this is 40.6, but in this direction. So if I go all the way around, 360 minus that, it's about 319.4 degrees, right? That's my angle. Okay. And then here, my angle, same thing. What's my angle here? Okay, so now I'm going to go the arctan of 1.2 divided by 1.7. And I'm getting about 35.2 degrees. That's roughly what that's going to be right there, about 35.2. All right, so now let's go ahead and find E1 and E2. We need to find those, okay? So let's find E1 and E2. So E1 is KQ1 over R squared. We'll go 9 times 10 to the 9 times 4, I believe it's 407. 407. Remember, we don't put the negatives in the equation, at least not the force and field equations. All right, divided by R squared, which is 1 point, I think it's 1.84. Let me see. 1 point plus 1.2 squared. Yeah, 1.84 quantity squared. So that's going to give us E1 and then E2, KQ2 over R squared. We'll go 9 times 10 to the 9 times 675. Oh, let me double check something here. Yes, okay, positive, negative. Okay, just had to double check the sign of my charges. So 675 times 10 to the negative 9 divided by 2.08 squared. Go ahead and find your values for E1 and E2. So for E1, I'm getting about 1,082. For E2, I'm getting about 1404, roughly. Okay, so now I need to find the components for these. Okay, and then from there, I can um, find the overall net field passing through point P. So we're going to find E1x and E1y. So E1x is going to be E1. E1 was 1082. So we're going to go 1082 cosine of 319.4. And we're going to find E1y. That's going to be 1082 sine 319.4. So we got to find those components. We have 821.5 and 1082 sine 319.4 It's about negative 704.1. Okay, so those are my components in the for E1, X and Y direction. E2, same thing. I'm going to find E2 in the X direction and E2 in the Y direction. Now, E2 was 1404. So we're going to go 1404 cosine 35.2. And we'll go 1404 sine 35.2. I'm getting 1147, the first one, and about 809.3 for the second one. Okay. Now to find your net field, I'm going to use Pythagorean theorem, and it's going to be EX squared plus EY squared. So I got to find EX and EY. So EX is going to be the sum of my X components. So it's going to be E1X plus E2X. Well, E1X is 821.5 plus E2X is 1147. So 821.5 plus 1147 is 1968.5. Now, E in the Y direction is going to be E1Y plus E2Y. So that's negative 704.1 plus 809.3. Negative 704.1 plus 809.3. It's about 105.2. Okay, those are your X and Y components. We'll throw those into Pythagorean theorem. And we're going 1968.5 squared plus 105.2 squared. At this point, probably want to pause the video and figure out your net field. I'm getting about 1971 newtons per coulomb. Now the direction, we're going to use the arctan formula. So it would be my EY 105.2 over my EX 1968.5. And I'm getting roughly about 3.06 degrees, so barely above the horizontal. Okay, like that. I mean, it's smaller than that, actually. All right. Enter my values in there. So 19, what I have? 1971, 71, and about 3.06. And there you go. Hopefully you were able to get question 3 right yourself. Now in our final question, we have a charge in an electric field. Now we need a brand new equation to help us with this when you go ahead and enter your name in the program, you're going to be given the distance between the plates. So mine is 51.5 millimeters. 51.5 millimeters. But I'm also given the voltage between the plates, otherwise known as the potential. Well, the potential between the plates is 1734 volts. Now, electric fields are always directed from positive to negative, so I can draw those. My electric fields would be pointing to the right. The value of that electric field I can also calculate too, because the electric field is the potential difference between the plates divided by the distance. In other words, 1734 volts over 0.0515 meters. So my electric field in this is going to be about 33,669.9, right? Volts per meter. Remember, that's the same unit as newtons per coulomb. Okay. All right, now we'll need that information to be able to do the problem. So now on this, we're going to calculate, we're going to draw all the forces that are acting on that ball. So I know that I have a tension going up like this. I'm going to break that tension up into its components, going up and over. This is my angle theta right here, which means this is also my angle theta. Well, the blue vector right here, that's the adjacent side of the triangle, so that would be t times the cosine of theta. The red vector up here is the opposite side of the triangle, that would be t sine theta. Well, there's an electric force that's pushing the ball away from the positive side of the wall, and that electric force is equal to QE. And then finally, there's the weight of the ball that's pulling down, and it should be balancing this component of tension, T cosine theta. And that's the weight equals mg. Okay, so for step 3, we need to show the calculations for the charge on the ball. And then ultimately, we got to come back and find the tension. So what I'm going to do is I'm going to, I'll do 2 calculations here. So I'm going to perform a system of equations, substitution, to get rid of tension. And then we will solve for charge. Well, I have 2 equations here. My first one is equation going left equals force going right. So force going left equals force going right. So that's T sine theta. So T sine theta equals QE. Okay, now my next one is forces going up balance and equal forces going down. So T cosine theta equals mg. Now, a really handy way to solve this particular system, especially when you have component vectors that involve sine and cosine, is to divide the 2 equations, especially divide the sine equation by the cosine equation, like that. If you do that, tangent cancels, and sine divided by cosine is tangent. So this becomes tan theta equals Q times E over M times G. Now you're trying to solve this equation for Q. So in order to do that, you need to multiply by the reciprocal of E over mg. which would be mg over e to both sides. Therefore, Q, was what you're looking for, is going to be equal to mg times the tangent of the angle divided by E. Let's put these values in our program. I know G is going to be 9.8 times the tangent of 31 degrees. The mass is 211 milligrams. Now, 211 milligrams. Okay, you got to convert milligrams into kilograms. If you remember your metric staircase, milligrams is all the way at the bottom, kilograms is all the way at the top. That means you have to move the decimal 1, 2, 3, 4, 5, 6 times in order to get that into kilograms. So it's 0.000211 kilograms. Okay, all that's divided by the electric field I found in the beginning, 33,669. Okay, let's figure out what this charge is. Wait, 0.000211 times 9, whoopsie, times 9.8 times tan 31. Divide that by 33,669.9. And I am getting 3.69 times 10 to the negative 8 coulombs. If I move this over 1, I get 36.9 times 10 to the negative 9 coulombs, which would be 36.9 nanocoulombs. Now I've got to find tension. Well, the good news is I've got two equations that have tension in, so pick your favorite one. I'm just going to choose the top one. T sine theta equals Q E. So in order to solve for tension, I need to divide away sine of the angle from both sides. So tension would be Q, which I'm going to use the actual value there. So 3.69 times 10 to the negative 8 times E, 33,669.9. Right? That's coulombs. That's newtons per coulomb. You can see coulombs cancels. Divided by the sine of the angle, sine of 31. Put that in our calculator. And I'm getting a pretty small tension of about 0.00241. Okay, now it wants me to enter my answer in millinewtons and nanocoulombs. So to get, this is in newtons. So to get millinewtons, I would have to move it 3 spaces to the right because newtons is a base unit. So that would be 2.41 millinewtons. All right, and there you go. Hopefully you were able to get question 4 correct yourself. I hope you found this tutorial to be helpful and serve as a good template to allow you to be successful in answering your questions. Thank you. See you next time.